Well, we're going to continue discussing resonance. Last time we discussed a little bit what resonance means and how to interpret it, and now we're going to get into the main task of how you can come up with the resonance arrows yourself. So we'll need to go over some rules.
Okay.
As usual in OChem, there's rules. So, and as usual, there might be some exceptions to some of these. So here's a rule. Do not break or form sigma bonds.
Okay.
That's something that should already be apparent from what we talked about yesterday. Now, there's nothing in OChem that says you can't break and form sigma bonds, but if you do that, it's just not resonance. That would be a reaction. So if we break or form any sigma bonds, those are possible arrows for a reaction, but not for resonance.
Okay.
So would this be a possible resonance arrow?
No, your tail of the arrow is coming from a sigma bond, which means it would break a sigma bond between carbon 2 and carbon 4.
Excellent. Good. And for that matter, it would also form a sigma bond between 4 and 5. Good.
Yeah.
So this is this a legal reaction arrow?
I believe so.
It doesn't. There's no reason we couldn't write that as a reaction arrow. So this is a reaction arrow. It's not a resonance arrow because it violates the rule we just talked about.
Yeah.
So would this be a legal resonance arrow?
Yeah.
Because it's breaking a pi bond and forming a pi bond.
Yeah. No sigma bonds really are involved.
Right. Is this a legal resonance arrow?
Yeah, you are only working with lone pairs and pi bonds. So,
Good.
yeah.
Is this a legal resonance arrow?
Yep.
Because again, we're only working with lone pairs and pi bonds. These electrons come from a lone pair. These are forming a lone pair. We're not doing anything with sigma bonds. Okay. I think that's pretty simple. So let's go on to rule 2. Now this should look familiar because this is one of the rules we talked about for drawing reaction arrows. This was also a rule for drawing reaction arrows, don't exceed an octet. And do you remember we tried to give you a straightforward way to tell whether you were exceeding an octet. So the idea was an atom with a complete octet cannot gain a bond unless it simultaneously loses a bond. Now, if we were talking about reactions, we would say that you can't gain either a sigma or a pi bond unless you simultaneously lose a sigma or a pi bond. But for resonance, we can be specific and say we're focusing specifically only on pi bonds, because otherwise it wouldn't be resonance. Tell me when you have that written.
Okay.
Okay. So like I say, this should look familiar because this is basically the rule that we learned for reactions, except that in a reaction, you would also include sigma bonds in this definition. Now, do you remember how we went over a way to tell whether an atom has a complete octet or not, because we don't want this to take too long to apply. It's been a while since we discussed this, but do you remember how can we tell whether an atom is already starting with a complete octet?
The charge typically will indicate that as far as the main elements that we're using with organic chemistry, except for the metals and semi-metals. So if it has a positive charge, it would be less, well, maybe that's not what it was. I know that is for some cases, but like a positive charge would indicate that it lacks electrons, but...
So would we say that this atom has a complete octet or an incomplete octet?
No, I think it actually does have a complete octet.
Okay, yeah, that's right. So now, in a way, it's good the way you were thinking because you were trying to use the charge to figure things out. We have said the charge is the most important factor, but in this case, I can see why you might think that a positive charge would give you an incomplete octet, but actually it usually doesn't work that way. So what we actually learned is almost all atoms have complete octets. Almost all atoms have complete octets. So all you need to do is just memorize the ones that don't have complete octets. It turns out to be very simple. There's only one atom that has an incomplete octet that matters for resonance, and that's C+.
Okay.
What do we call a carbon with a positive charge?
Carbocation.
Yeah, so carbocations are going to be the only ones with incomplete octets that matter for resonance. Okay. You can basically assume that everything else has a complete octet.
Okay.
So, to go back to the example we were talking about, does this have a complete or an incomplete octet?
It has a complete octet.
Because it's not C+.
Yeah.
That's a pretty simple rule to apply. Even though it has a positive charge, it still has a complete octet. So does this atom have a complete or an incomplete octet?
Incomplete.
Because it's a carbon with a positive charge.
Yeah.
So this has room for a new bond.
Okay.
Does this have a complete or an incomplete octet?
It has a complete octet.
Despite the positive charge, because it's not a carbon with a positive charge.
Yeah.
Does this atom have a complete or an incomplete octet?
Complete.
It's a carbon, but it doesn't have a positive charge, so it's still a complete octet.
Okay.
Okay, now when we went over reactions, we saw some other atoms that have room for more electrons. For example, we saw H plus has an incomplete doublet, so it has room for more electrons. But that's not an issue for resonance because an H plus is not bonded to anything else. So there can't be any resonance structures for H plus, so we don't need to worry about H plus here. I think we also mentioned that neutral metals and semimetals have incomplete octets. In fact,
Yes.
I think we were reviewing that just recently because we saw these were Lewis acids. We saw these are Lewis acids because they have incomplete octets. But I don't think I'm going to write them down here because I can't think of any examples of resonance that involve metals and semimetals. I can't think of any examples of resonance that involve metals or semimetals, so I don't think we need to review those for this topic. So they also have incomplete octets, but I don't think so that's why I said the only atom with an incomplete octet that matters for resonance is C+. So this has an incomplete octet because it's a metal, but it doesn't really matter for resonance. So I think this is the only one we need to put in. Okay. Okay, so is this resonance arrow legal or illegal?
It's illegal because that carbon already has a complete octet. In order for it to receive that new pi bond, it would need to also lose a bond, but it's only got sigma bonds, so it's illegal.
Okay, that was a good analysis. So you actually did a two-stage analysis. The first stage was you said the way it's drawn, this is illegal because carbon-2 is gaining a pi bond without losing a pi bond. And then you went the extra mile and you went to stage 2 and you asked whether there was a way you could fix this. And you said you can't even fix this because the only way to fix this would be for carbon-2 to lose a pi bond. And carbon-2 doesn't have any pi bonds. So not only is this not legal resonance, you can't make it into a legal resonance by adding a second arrow. You could make it into a legal reaction. This would be a legal reaction, but now it wouldn't be resonance. Okay.
Okay.
So that was a good analysis. Good.
Thanks.
Is this legal or illegal? Whoops. It's nothing. Is this a legal or illegal resonance?
That's legal because the carbocation has an incomplete octet, so it can have a new pi bond formed.
Okay, that's right. By the way, notice that it's good that you're noticing this very clearly. This arrow is not pointing directly to carbon-2, but it does mean carbon-2 is gaining a new bond. So that's good that you saw that. Are these arrows legal or illegal?
Legal.
But wait, carbon-2 has a complete octet. How can it be gaining a new bond, a new pi bond, if it has a complete octet?
It's breaking a pi bond, or it's losing a pi bond, so it's
so it's not going to violate the octet rule. So it is possible for an atom with a complete octet to gain a pi bond if it simultaneously loses a pi bond. Carbon-2 is legal because it's both gaining and losing a pi bond at the same time. What about carbon-3? Carbon-3 starts with a complete octet, and it's gaining electrons, so why doesn't it violate the octet rule?
Well, it's not actually gaining any more electrons than it already had. It had the equivalent of those same electrons. It had a pi bond, and that completed its octet. I'm not wording it the best way, but
it's hard to put it into words, but yeah, I can see you're on the right track. Good. This is a little bit of a subtle issue. So there's a long way and a short way to think about this. The long way is it's true that carbon-3 started with a complete octet, but all it's doing here is it's just taking the pi bond and turning them into a lone pair. Either way, it'll still have a complete octet. It's not really gaining any electrons. So I guess here's the point. For purposes of the octet rule, carbon-3 is not gaining these electrons because it already had them in the pi bond. This is a little subtle because for some purposes, we would say carbon-3 was sharing these electrons before. But for purposes of the octet rule, we would just say it already had those electrons in its octet. Yeah. Okay, now that's kind of a subtle reasoning, though. So it would be nice if we could see a quicker way to see this was illegal without thinking about it so carefully. And maybe you already did that. The point was the only way to break the octet rule is by gaining a bond. You can't break the octet rule by gaining a lone pair. If we just memorize that as a rule, that'll save us some time. And perhaps you were already kind of applying that. So we don't have to even worry about carbon-3 because it's not gaining a pi bond. The only way to break the octet rule is by gaining a bond. Carbon-3 is gaining a lone pair. So another way of putting it is you never break the octet rule by gaining a lone pair. We were just trying to explain why that was, but we found it was a little bit hard to put into words. So maybe it's better just to memorize it. You can never break the octet rule by gaining a lone pair. You can only break the octet rule by gaining a bond. So anyway, what you said before was correct. This is legal. Okay.
Okay.
Legal or illegal?
I think that's illegal. The nitrogen already has a complete octet.
How do you know it has a complete octet?
It's not a carbocation.
Yeah, it's a pretty easy rule. It's not carbocation, so it has a complete octet. Good, so that would be illegal. Excellent. Is this legal or illegal?
That's illegal. You'd have to break a pi bond in order for it to that carbon on the carbonyl, carbon 4. In order for that to receive a new pi bond, it would have to simultaneously break a pi bond.
Okay, good. So yeah, this is not legal because 4 is gaining a pi bond without losing a pi bond. Is there any way to fix this so this would be legal resonance?
Yeah, you could have it break a pi bond with oxygen, and oxygen receive a lone pair.
Now carbon 4 is both gaining and losing a pi bond, so it won't break the octet rule. By the way, notice this would leave carbon 2 with an incomplete octet, but that's okay. It's okay to have an incomplete octet. It's just not allowed to have a more than a complete octet. Okay, good. Is this a legal or an illegal resonance arrow? There's no arrow. All right. How about this?
Illegal.
And why is that?
Because it's trying to form a bond, a pi bond with carbon-3, without simultaneously losing a pi bond.
Okay, good. One moment. So is this legal or illegal resonance?
Illegal. It's breaking a sigma bond.
That's right. So so here I switched things up and switched back to the first rule. This is illegal. It doesn't. Does this violate the octet rule? Actually, it still violates the octet rule too.
Yeah.
But it's also going to be illegal because it's breaking a sigma bond.
Yeah.
Would this be legal or illegal resonance?
Illegal. It's breaking a sigma bond.
Okay. It's actually a legal reaction arrow. This would be legal, although maybe not very favored as a reaction, but it would be possible as a reaction, but it's illegal resonance because it's breaking a sigma bond. Is this legal or illegal resonance?
Legal.
This atom is not breaking the octet rule. Why not?
Because it's okay to receive a lone pair of electrons.
Yeah.
It's not forming any bonds.
Yeah, it's not forming a bond, so it can't be breaking the octet rule. Good. Is this legal or illegal resonance?
Looks legal to me.
The nitrogen is gaining a pi bond, but it's also losing a pi bond.
Yeah.
Good. Okay. That's rule 2 here. I think we will see a kind of an exception to this eventually, but we'll get back to that later. So then rule 3. Does nature like or dislike charges?
Dislikes charges.
Dislike charges. However, the whole point of resonance is to discover the hidden charges. So it's not like we're going to avoid drawing charges for resonance. It's okay to create charges, but we should do not. We don't want to go overboard. We don't want to have 3 charges in the same resonance structure. Do not create resonance structures with 3 charges.
Okay.
So 2 charges can be okay. 2 charges can be okay, but 3 charges, no. If you remember the work that we did on reactions, we did sometimes see reactions where a molecule had 2 charges. I don't think we saw any reactions where a molecule had 3 charges. So generally in OChem, we're not going to have molecules with 3 charges, although sometimes we can have 2 charges in the same molecule. Okay, good.
Okay.
So is this a good or a bad resonance arrow based on that rule?
That's okay.
How many charges would that create?
2. It would create a carbocation and a negative charge on the oxygen. Yeah, okay, that's right.
Is Is this a good or a bad resonance arrow?
Bad. You'd end up with 3 charges.
On where?
On the oxygen, it would have a negative. Carbon-2 would have a positive charge, and carbon-3 already has a negative charge.
That's right. Now, this rule is a little bit different from the earlier rules, because these earlier rules kind of were told us what was legal or illegal. It's just completely illegal to break or form a pi bond for resonance, because if you did that, it wouldn't be resonance. It would be a reaction. And it's completely illegal to break and exceed an octet. That's just something that can never happen in nature for most elements. Here, though, we wouldn't say this is illegal resonance. We would say technically it's insignificant resonance. So there's some resonance structures that are possible, but are extremely insignificant. That is, they don't play a big role in determining the structure of the molecule. Do you remember that we saw earlier that resonance should be, what resonance gives you is 2 pictures that you blend together to imagine what the real picture is like.
Yeah.
For example, up here, does the oxygen really have a positive charge or not? Well, the answer is that the oxygen is a blend of these 2 pictures. It has a partial positive charge. It has a partial positive charge because the real picture is a blend of these 2 pictures.
Or it would be a partial negative, right?
Excuse me?
It would be a partial negative charge.
Who would have the partial negative?
The oxygen.
On this example? Oh, you are correct. Thank you. I messed up. Thanks. That's important.
Makes sense.
That's good that you saw that. Okay, yes. So the oxygen should have a partial negative charge. That's right, which is a blend of these 2 pictures. Okay, so the real picture is a kind of weighted average of these 2 pictures. The real picture is a kind of weighted average of these 2 pictures. But that doesn't mean they get equal weights. I would suppose this picture gets a greater weight because you prefer the neutral picture to the charged picture. So we wouldn't necessarily say the oxygen has a -1/2 charge, because that would be equal weights. I'm just making up something up, but maybe the oxygen has maybe a -1/4 charge, and carbon-2 has a +1/4 charge, because maybe we should put more weight on the neutral picture. Well, this picture here, it's not that this resonance is impossible. This resonance is possible. This is one of the resonance structures, but with 3 charges, it's extremely insignificant. So it would have almost no weight. There would be almost no weight put on this resonance structure. So I don't know, you might put, say, make it extreme, 98% of the weight on this picture and only 2% of the weight on this picture. Well, when something is getting so little weight, it has almost no effect on how the molecule will react. So that's a little bit of a subtle point. But when we say this is a bad resonance arrow, it's not that it's completely illegal, but it's giving us a resonance structure that is so insignificant that there's no point paying attention to it in OChem. In OChem, we only want to pay attention to the relatively significant resonance structures. And this is so insignificant that we can basically ignore it. So that's why it's a bad arrow, not because it's illegal, but because it's not helpful to us. Okay. But in any case, the point is it's better not to draw it. Not because it's illegal, but because it gives us a completely insignificant structure. So it's still bad. There's no point in drawing it.
Okay.
So would this be good or bad resonance arrows based on the rules we've talked about so far?
Good. Much more significant than the previous one.
How does this fix the problem from the previous example?
Well, this actually only leaves you with 2 charges in the end. Well, actually, no, not even 2. It's just 1 charge on the oxygen, a negative charge.
So this arrow was bad because it created 2 charges in addition to this one. But this arrow is okay now because there's still only going to be 1 charge.
Yeah.
So what are the resonance structures of this molecule? Here's a resonance structure. Here's a resonance structure, and this is a possible resonance structure too. These are all possible resonance structures, but the point is this one is just so insignificant that there's no point drawing it. Remember that the true structure is a kind of weighted average of all of these resonance structures. Actually, there's even more we could draw, but let's just focus on these three. But the point is that this one and this one are going to get almost all the weight. So you might say that the true structure of the molecule is based on, I don't know, it's based on maybe, let's see, what's 98 divided by 2? That would be 49. So maybe 49% of the weight on this structure, maybe 49% of the weight on this structure. They wouldn't really be equal, but just say they're equal. 49% on this structure, 49% on this structure, and only 2% on this structure. Well, then this one is so insignificant that there's no point drawing it in the first place. Okay.
Yeah.
So not only do we want to avoid illegal resonance structures, but we also want to avoid drawing ones that are completely insignificant. So this is bad, not because it's impossible, but because it's so very, very insignificant in the weighted average. Okay? By the way, compare. These are interesting to compare right here. Do you see how similar they are? This was legal. It's okay to make 2 charges, but not if there's already a 3rd charge existing.
Okay.
It's okay to make 2 new charges. 2 charges is okay, but you can't do that if there's already a 3rd charge, because then that would give you 3 overall. Okay? Okay, so don't create resonance structures with 3 charges. There is one exception to this rule again. I don't know if we're actually going to bother talking about that. Maybe we'll get to that later. Okay. I think that's it. So those are our rules for resonance. These are the rules for resonance. Like I say, there are 1 or 2 exceptions we might get to later, but these are pretty solid rules for resonance. All right? So how are we going to learn? So the next thing is I want to just go into how you can draw the resonance arrows. How can you come up with the resonance arrows? We're going to do this a little bit differently than we did reactions. With reactions, we kind of went over, tried to predicting what roles things would play. Nucleophile, electrophile, leaving group, acid and base. But for resonance, I think the best approach is just to recognize about 5 different patterns. We're just going to memorize 5 patterns that come up for resonance. And once you've learned how to recognize those, you should be able to draw the electron-pushing arrows. So here's our first pattern. A lone pair on an atom that is adjacent to an atom with a pi bond. Tell me when you have that down.
Okay.
So this would be an example of that pattern. Okay, so here's an example of this pattern. A lone pair on an atom that is adjacent to an atom with a pi bond. And I'll show you what the electron pushing arrows look like for this. So would this be legal?
No.
Why not?
You're violating an octet rule.
Right. So how can we fix this?
You would need to break the pi bond, giving carbon 3 a lone pair.
So you can see why a lone pair is not enough. It's got to be a lone pair that's on an atom that's adjacent to an atom with a pi bond. If carbon 2 had not had the pi bond, there's no way to fix this arrow. There's no way to fix this arrow because there's no pi bond to break on carbon 2. So you can see why in this pattern we need not just the lone pair but also the pi bond.
Yeah.
Okay, so now these would be legal resonance arrows. Okay, good. Okay, so let's try coming up with legal resonance arrows for this picture on your screen.
Okay.
Okay, excellent. So this is the same pattern of a lone pair on the oxygen that's adjacent to carbon-3 with the pi bond. This is a little tricky because here we didn't draw in the lone pair on the oxygen, but I think we've learned previously that negative charges often represent lone pairs, and that's the case here. This negative charge represents a lone pair, so we don't actually have to draw the lone pair. This is still the same pattern as before. Okay, excellent. Why don't you go ahead and draw the resonance structure you would get from this?
Okay.
Okay, excellent. Outstanding, that's right. So I'll go back to my screen. Okay, well, let's try this example. Try to come up with some electron-pushing arrows here.
Okay.
Great. Perfect. So again, we have the lone pair on carbon-2 that's adjacent to carbon-3 that has a pi bond. So go ahead and draw the resonance structure you would get from that. Okay, great. Now, why does this matter? Why do we care about this? How is this interesting? So what role would you expect this molecule to play in a reaction? What role would you expect this molecule to play in a reaction?
Base or nucleophile.
Excellent, because of the negative charge. Negative charges make things basic or nucleophilic. Who would you expect to be the nucleophilic atom? Who would you expect to be the nucleophilic atom?
Probably carbon-4.
Because it has a negative charge.
Yeah.
Right? Now, actually, so the answer I was going for is either 2 or 4. Because
Okay.
there's resonance, both of them have resonance structures where they have negative charges. So either 2 or 4 might be the basic or nucleophilic atom.
Okay.
So the point is, we're starting to see why resonance is useful, because if all you saw was the picture on the left, you wouldn't have any idea that carbon-4 was nucleophilic. So this is the whole point of resonance. It reveals hidden charges. What's the most important factor in organic chemistry?
The charges.
So we don't want any hidden charges that we don't know about. We want to know about all the charges. Just like, I don't know, you don't want any hidden money under the cushions in your couch that you don't know about, right? Money is really important. You don't want it hiding away. You want to know where your money is. Well, in OChem, charges are what are important. So you don't want any hidden charges that you don't know about hiding under the couch cushions. So, I don't know, resonance is like turning over the couch cushions and finding those hidden charges, finding the hidden money. Okay. So a naive student would say, aha, I know what's going to happen here. Carbon-2 will be the nucleophile. But the sophisticated chemist knows that there's another resonance structure and maybe carbon-4 will be the nucleophile. Now, you tried to go further and figure out which one would be the nucleophile, but we're not going to worry about that right now. Oftentimes, that's hard to predict. You'd have to kind of like memorize the details of specific reactions. It's actually pretty hard to predict from general principles which resonance structure will govern the reaction. It's hard to predict from general principles which resonance structure will govern the reaction. So you just have to learn that when you study the individual reactions. There aren't really any good general rules. One thing that doesn't really work, you might think that the more significant resonance structure would govern the reaction, but sadly it doesn't work that way. Even if a resonance structure is somewhat less significant, it can still be the one that determines what's going to happen in the reaction. Now, if a resonance structure was completely insignificant, if it was only getting like a 1 or 2% weight, like the example we talked about a few minutes ago, then that wouldn't determine the reactivity. But if two resonance structures both are fairly significant, just because one is a little less significant doesn't mean it can't determine what will happen. So all we can say here is either 2 or 4 could act like a base or a nucleophile. Okay, I'll go back to my screen. See if you can come up with another resonance arrows for this structure.
Okay.
Great, and let's draw the rest of the new structure.
Okay.
Okay, excellent. Now, here is very important, you put in the positive charge on the nitrogen. That's something that I think people tend to forget. For some reason, when there's a neutral atom at the beginning of the arrows, people tend to forget the positive charge. So that's very important that you remember to put in that charge. How many charges should we change on for every new resonance structure?
2 charges.
Yeah, for every new resonance structure, we're going to change 2 charges. That's similar to the rule that we learned for reactions. Good. Also, the other way you can double check, what was the total net charge of the first resonance structure?
The total net charge of the first resonance structure appeared to be 0.
That's true. And what was the total net charge of the second resonance structure on the right?
Also 0.
Because positive 1 minus 1 is 0. That always has to be the case. The total net charge of all the resonance structures always has to be the same.
Okay.
If they're not, then you made a mistake. If you ever have a resonance structure with a different net charge than the other resonance structures, you've made a mistake. But in a way, we don't even have to check that if we just remember to change the 2 charges for each resonance structure. Now, what can we predict about reactivity here?
Well, it looks like carbon-2 appears to be the most nucleophilic because it has a partial negative charge, whereas nitrogen, although it typically could be a nucleophile with its lone pair, it actually has a partial positive charge. So it looks like carbon-2 might be the better suited nucleophile.
That's a very good analysis. That's exactly the right way to think about that. Excellent. This is a little different from the earlier examples, but that's a very good way to think about it. So first of all, basically we would expect here carbon-2 to play the role of nucleophile. Or what other role could it play?
Base?
Yeah. So probably here what's going to happen is that carbon-2 will be a nucleophile or a base. Maybe I'll go back to my screen. Now, what would a naive student think? Now, notice if you go back to my screen, that's kind of maybe a little counterintuitive. You wouldn't from this picture. Although even here, you would already expect maybe carbon-2 to be nucleophilic a little bit because of the carbon-carbon pi bond. But
Yeah.
here you would say, gee, maybe the nitrogen should be a nucleophile because of the lone pair.
Yeah.
However, as you were saying, it probably won't be a nucleophile because it actually has a hidden positive charge. Do positive charges make things more or less nucleophilic?
Less.
Much, much less. So generally speaking, if there's any resonance structure where you have a positive charge, you're probably not going to act like a nucleophile.
Okay.
If there's any resonance structure where you have a positive charge, you're probably not going to act like a nucleophile. So this is a good case example of how resonance can help us out and help us to avoid mistakes. At first, you might not be sure whether, in this case, first you might be leaning towards thinking of the nitrogen as the nucleophile here. But that doesn't make sense because it has a hidden positive charge, so we can be fairly confident that carbon-2 will be the nucleophile. Or what other role could carbon-2 play?
Base.
Right. Good. Here's benzene. What role do we expect benzene to play in a reaction?
Could be a poor nucleophile.
Is it a good nucleophile or a poor nucleophile?
A poor one?
Yeah, we said earlier it's a poor nucleophile because it has what's called aromaticity. It's actually especially stable. So it could be a nucleophile, but it's not that good one. See if you can draw another resonance structure for this molecule.
Okay. Hmm. Okay.
Very good. Again, it's good that you remember to change two charges. That's crucial. Why don't you number the carbons so it's easier for us to refer to them?
Sure.
Numbering the carbons is a little less important for resonance than for reactions because because we're making smaller changes, so it's not as easy to make mistakes. When you're doing a reaction, it's always crucial to number all the carbons to make sure you don't mess up the carbon chain. In resonance, you're not really changing the carbon chain, so numbering is not as important. But anyway, it's helpful to number here so we can just refer to these more specifically. Okay, yeah. Good. So let's see, where were we? So that's excellent. That's good resonance. This is the same pattern we've been talking about. A lone pair on the oxygen, which is adjacent to carbon 1, which has a pi bond. So what reactivity would you predict here?
Well, you definitely would not have any nucleophilic activity coming from oxygen.
Which you might have thought at first. At first, you might have thought the oxygen would be a nucleophile with its lone pair, but it now has a positive charge. We know neutral oxygens are not great nucleophiles to start with anyway. But anyway, I think generally things that have a positive charge in any resonance structure are not going to act like nucleophiles. So very good. Okay, so who would be reactive? Who would be the reactive atom?
One of them looks like could be carbon 6.
Excellent. What role would it play?
Nucleophile or base. Good,
that's right. In this case, probably a nucleophile, but yeah, with a negative charge, you would think of a nucleophile or a base because it has that hidden negative charge. So basically, we're saying that the benzene could be nucleophilic. Yeah. Well, remember we already said that benzene was nucleophilic, but is this benzene going to be more or less nucleophilic than a normal benzene?
More. It has a hidden negative charge.
That's right. So here's another payoff from drawing the resonance structures. Remember we said that kind of a naked benzene with nothing attached to it was only a poor nucleophile.
Yeah.
But this is now going to be a stronger nucleophilic benzene because it has that hidden negative charge. I'll go back to my screen. What would happen if you put benzene together with, say, Br2?
Nothing.
We talked earlier, there would be no reaction here. Br2 actually is somewhat electrophilic, but it's not electrophilic enough to react with a poor nucleophile like this. Do you remember, what did we say we had to do to get a reaction to happen here?
You could add a strong acid to make a better electrophile out of Br2.
Right. What we added were, in these cases, we added what were called Lewis acids. Good. We added this Lewis acid. We need a Lewis acid. And we saw that that would make the Br2 positive, which would make it more electrophilic. Now, is this a better or worse nucleophile?
Better.
Yeah. In fact, this doesn't need the catalyst.
Okay.
This is, again, something that you go into in more detail in the second semester. This reaction would take place even without a catalyst. And we can explain that in terms of the resonance.
Okay.
Let's go back to your screen. Something else. Which atom are we predicting would be nucleophilic here?
Well, it actually looks like carbon 6, 4, or 2. If you were to draw the other resonance structures, any of those have a hidden negative charge.
Okay, looks like you're on the right track. Great. So first of all, we would predict maybe carbon 6 would be nucleophilic with a hidden negative charge. But I think what you're saying is that there's more resonance structures we haven't drawn yet.
Yeah.
So let's try to continue. Try to draw new arrows that will lead us to a third resonance structure.
Okay.
Those are good arrows. That's the same pattern as before. Now there's a lone pair on carbon 6, which is adjacent to the pi bond on carbon 5. Excellent. So let's continue and draw that structure. Great. Okay. Excellent. Can we draw any more resonance structures?
Yeah.
Okay, excellent. Can we draw any more resonance structures?
So technically I don't know that this would be different from the starting material. You could return that negative charge, I guess, back up where it came from.
So let's draw the arrows first.
Oh yeah, sorry.
Okay, but you're already seeing that's pointless because that'll just take us back to the first picture.
Yeah.
So those are legal, but there's no point drawing them because that would just repeat the first picture. Okay, so basically, are there more resonance structures? No. Those arrows you drew are legal, but there's no point drawing things that'll just take us back to the first picture. So overall, we came up with 4 different resonance structures here. Great. So who do we expect to be the reactive atoms here? Who might be reactive?
Carbons 6, 4, or 2.
Good. And what role would they play?
Nucleophile.
Excellent. Good. Very good. So notice how powerful this technique is. Not only is the benzene more or less nucleophilic than it would be without the OH?
It's more nucleophilic with the OH.
But not only that, how about carbons 5 and 3 and 1? Do we expect them to be nucleophilic?
I guess they could be. They have a pi bond.
Okay, that's true. More or less nucleophilic than carbon 6.
Less.
Yeah, so the key thing is we would expect 5, 3, and 1 to be much less nucleophilic than carbon 6, 2, and 4. But actually your answer was a good one. carbon-5 still can act like a nucleophile. That's just not going to give us the major product. Okay. So this is a really good example of how powerful resonance can be. It's not only predicting that some of the carbons in benzene are more nucleophilic than before, but it's telling us exactly which ones. This is something that's kind of amazing, that we can draw these pictures, like just with pencil on paper, on a piece of paper, and then these weird resonance pictures, and this is actually how the molecule behaves. If you actually do the test on this molecule of benzene, you will really find that the reaction occurs the great majority of the time at 6, 2, and 4, and not 5, 3, and 1. Somehow these silly little pictures that we're drawing on the piece of paper really do, with these silly resonance rules, really do predict how the molecule is going to behave. Sometimes it's interesting to step back and think how amazing it is that we can actually predict what will happen in real life with these little rules and these pictures. So this really does work. Okay, good. Let's see.
So, quick question.
Yeah.
Carbon 1, that wouldn't necessarily play any role of, like, electrophile, would it? With that oxygen being a pseudo-leaving group?
That's a really good question. That certainly would be consistent with the rules we talked about earlier. That's right. The rules we said earlier would say that carbon 1 should be electrophilic. However, it turns out, I haven't been emphasizing that because that's not how it actually behaves. It turns out that what will happen is that we'll be using 6, 4, and 2 as nucleophiles. One thing you might notice is, that there's a bunch of pictures where carbon 1 is next to a negative charge.
Yeah.
Would that make it more or less electrophilic?
Less.
Yeah. So maybe in this case we could justify that. It's not only next to a positive charge, it also has a bunch of resonance structures where it's next to negative charges.
Yeah.
So we might not expect it to be particularly electrophilic. So it turns out that in real life it is going to be the nucleophile reactions that happen here. But I can see how we might consider carbon 1 to be an electrophile based on what we talked about before. So that's a good thing to have noticed. Okay. Okay. Good. So that's correct here. So it turns out that the 2 and 6 positions are called ortho positions in benzene, and the 4 position is called para. So the OH group here would be called an ortho-para director, because it tends to make 2, 6, and 4 active. That's something, again, that you go into in the second semester. Okay, and now we're able to predict that. Okay, good. I'll go back to my screen. One thing you've been doing here is you notice that the O started with a lone pair, even though I didn't draw it. So how do you know which atoms have lone pairs? You probably started to get a feel for that, but maybe we should make a note. I don't know. Maybe I'll write it here. Basically, when we're talking about an atom with a lone pair, we're usually going to be talking, well, we're usually talking about
the NOPS, were those the ones that we mentioned before?
Those are pretty important, yeah. Also, neutral halogens have lone pairs, but resonance is often not too important for those.
Okay.
And also, when a nonmetal has a negative charge, it would have a lone pair. So the atoms with lone pairs are neutral atoms from the nitrogen, oxygen, and fluorine columns, although halogens often don't play very strong roles in resonance.
Okay.
And any nonmetal with a negative formal charge has a lone pair. Okay. So does this fit into the pattern we were just talking about? An atom with a lone pair next to a pi bond.
No.
No, it doesn't fit into it because it's not really next to the pi bond.
It is the pi bond. It has the pi bond.
It's supposed to be adjacent to an atom with a pi bond, not on the atom with the pi bond. So this would not fit that pattern. You can see this is breaking the octet rule because this atom is gaining a pi bond without losing a pi bond.
Yeah.
So the pattern looks like this, not like this. Okay?
Okay.
Okay, I think we're getting the idea of that pattern, so let's add another pattern. Okay, so here's our next pattern. A lone pair on an atom that's adjacent to a carbon with a positive charge. Tell me when you have that down.
Okay.
Okay, so let's see if we can come up with electron pushing arrows here. You can try that on your screen.
Okay.
Okay, perfect. Excellent. Very good. By the way, I haven't been emphasizing it, but notice how these arrows also are kind of consistent with what we talked about before for reactions. Notice that the arrows start on a lone pair. We often see that, and the arrows tend to move. Are the arrows going to tend to point towards positive or towards negative charges?
Positive.
And are they going to tend to point towards or away from negative charges?
Away from.
Yeah. So I've kind of just been taking that for granted because we got so used to that with reactions. but that's certainly something that can help you to predict what's going to happen with the resonance. The electron pushing arrows are generally going to point towards positive charges and away from negative charges.
Okay, yeah.
Okay, that's something that hopefully is so much second nature to us now that we kind of do it without even thinking about it. But we're going to continue to want to have arrows that point away from negative charges and towards positive charges. Okay, so that was a good example here. So here we have a lone atom with a lone pair, which is attached to this carbon with the positive charge. That fits into the pattern we were just talking about. Okay, so let's see if we can come up with electron pushing arrows here.
Okay.
Okay, good. Compare this with the previous example. In both cases, they're similar. In this case, we didn't actually draw the lone pair on the oxygen, but we know that anytime a non-metal has a negative charge, it has a lone pair. So this still fits into the pattern that we saw earlier. Good. I'll go back to my screen. So would this be legal resonance?
No. That carbon 2 still would need to lose a pi bond in order for it to receive a pi bond.
That's right. So how could we make this legal? Well, now we're seeing two ways this could be legal. This could be legal if carbon 2 had a pi bond to lose at the same time as it was gaining. Or it could be legal if it started with a positive charge.
True.
So this does not break the octet rule. Why does this not break the octet rule? Because a carbon with a positive charge starts with an incomplete octet, as we saw earlier. So it has room for it. It can gain a bond without losing a bond. And this is not illegal because even though it started with a complete octet, it's also losing electrons in this bond. Okay, good.
Okay.
So would this be legal or illegal?
That's illegal.
And why is that?
Well, nitrogen with positive charge does not mean it has an incomplete octet. Only carbon with a positive charge would be okay there.
That's right.
Yeah.
Good. So that's why if you go back to the rule, notice we didn't just say that the lone pair has to be on an atom that's adjacent to an atom with a positive charge. It's not good enough to be adjacent to an atom with a positive charge. The only way that there's going to be room for the lone pair to move in is if it's adjacent to a carbon with a positive charge. So the word carbon here is important. So we could have said a lone pair on an atom that's adjacent to a carbocation is this rule. Okay? This seems very reasonable. We got negatives moving towards positives, but even though it seems reasonable, it's illegal because it breaks the octet rule. Okay?
Yeah.
Okay, so let's see if we can come up with reasonable resonance arrows here. Let's try that on your screen.
Okay.
Okay, excellent. Okay, very good. So let's try to predict something about the reactivity here. How would we expect this molecule to react?
Electrophilically, carbon 2. Well, it's kind of tricky because carbon 2 on one hand with the positive would be electrophilic, but over here it has a pi bond, which is more nucleophilic. So I'm not sure actually. Nitrogen on the left would seem more nucleophilic, but on the right would not appear nucleophilic at all.
Okay.
Not quite sure.
Okay, so let's try to clarify that. So first of all, yes, the nitrogen probably will not be a nucleophile here. Because there's a resonance structure where it has a positive charge. So we would not expect the nitrogen to be nucleophilic despite its lone pair. Now, I think you said you might think the carbon-2 might be a nucleophile. What made you say the carbon-2 might be a nucleophile?
Yeah, the nucleophilic pi bond there.
Okay.
Now, actually, we usually talk about carbon-carbon pi bonds as being nucleophilic. So.
Okay, you took the words out of my mouth. Good, that's right. So it actually is a mistake to say that pi bonds are nucleophilic. It's a mistake to say that pi bonds are nucleophilic. As you were just saying a second ago, it's carbon-carbon pi bonds that are nucleophilic. So it can be kind of tedious to always say carbon-carbon pi bonds instead of pi bonds, but there's actually a difference. It's carbon-carbon pi bonds that are nucleophilic, not just any old pi bond. So let me help you a bit with this. Let's just start by focusing only on the left-hand structure. If you just look at the left-hand structure, what role would you expect that left-hand structure to play in a reaction?
Electrophile.
And who would be the electrophilic atom?
Carbon 2.
And why is that?
Because of the positive charge.
That's right. Even without the resonance, you wouldn't expect the nitrogen to be a nucleophile because remember, you want to use the charges. So even without the resonance, we would have expected from the left-hand structure that carbon-2 would be an electrophile. Now, let's just look at the right-hand structure. Ignore the left-hand structure. If all you had in front of you was the right-hand structure, let's just use the rules that we've already talked about. Based on the rules that we've talked about earlier, what role would you expect the atoms in that right-hand structure to play?
I think you'd still expect carbon-2 to be an electrophile because it is attached to a molecule with positive charge.
Attached to an atom with a positive charge. Yes.
Or atom, yeah.
Okay,
Thanks.
yes. So that's what I think you were missing a second ago. When you were looking at this before, you thought carbon-2 would be a nucleophile because of the pi bond. But we've seen that's actually a misunderstanding because it's not a carbon-carbon pi bond. So actually, both resonance structures here predict the same reactivity, is my point. This is a little different from the earlier examples. Both resonance structures here predict the same reactivity. Why would you not expect the nitrogen with the positive charge to be an electrophile? Well, we've discussed that actually, usually when there's an atom with the positive charge, it's the attached atom that's the electrophile. Yeah. Except when the positive charge is on a carbon. Yeah. So if you look at so those rules we talked about actually work very nicely here. If you look at the left-hand structure, there's a positive charge on a carbon. Well, we know that tends to make the carbon electrophilic. And if you look at the right-hand structure, there's a positive charge on the nitrogen. Well, we know when there's a positive charge on anything besides a carbon, it's the attached atom that's the electrophile, which would still be carbon-2. So one thing we're saying here that in this case, the resonance does not really change the reactivity. We would predict the same reactivity from both pictures. Okay. Maybe I'll go back to my screen.
Okay.
Do you still have this handout?
Yeah.
Okay. So I just wanted to review a couple things we had a little trouble with here. So notice that what we learned makes something nucleophilic is a carbon-carbon pi bond. Maybe I didn't emphasize this as much as I should have, but not all pi bonds are nucleophilic. Carbon-carbon pi bonds are nucleophilic. Also, what we were using here was these rules for for positive formal charges, the rules for positive formal charges. When the positive charge is on a carbon, the carbon is the electrophile, like in your left-hand resonance structure. But when the positive charge is on anything besides a carbon, the atom that's attached is the electrophile. Okay.
Okay.
Let's go back to your screen. So in a way, you might think the resonance was a little bit unnecessary here, because we got the same prediction in both cases. But here's where it comes in handy. What is carbon-2? What type? Let's look at the left-hand structure. Carbon-2 is a carbocation. Is it a primary, secondary, or tertiary carbocation?
Primary.
What's the definition of a primary carbocation?
It is only attached to one other carbon.
That's right. Good. So you got that correct. A lot of people say carbon-2 is secondary because they count the nitrogen. But that's not the way the rules work. Primary means attached to one carbon chain. Secondary means attached to two carbons, not two things. So carbon-2 is a primary carbocation. Now, are primary carbocations usually possible or impossible?
Impossible.
Usually we don't form primary carbocations. So why are we even bothering with this? Why are we even bothering with this picture if it's impossible? Is this possible or impossible? So, so I'll just say this is an exception. In this case, it's okay to have the primary carbocation. What is it that's making it okay to have a primary carbocation here?
Resonance.
So does the resonance stabilize or destabilize the positive charge?
Stabilizes it by
That's
spreading.
right. So in fact, primary carbocation here is okay. So this is an exception to the rule we talked about earlier. Earlier we said avoid primary carbocations. But the exception is primary carbocations are okay if they're resonance stabilized.
Okay.
So that's how the resonance is helpful here. The resonance doesn't really change the reactivity, but without the resonance, we wouldn't even have expected that this could happen in the first place, that we could get this structure in the first place. Without the resonance, we wouldn't even realize that this was a possible structure. Okay, so remember, does nature like or dislike charges?
Dislikes charges.
So what does nature try to do with charges? Does nature try to concentrate charges or spread them out?
Spread them out.
That's why resonance is good. Resonance is good because it's spreading out the charge. Remember, if you look at the left-hand picture, you might think there was a full positive charge on carbon-2. But what we know, in fact, is that the true picture is a blend of these two resonance structures. Carbon-2 is a blend of a picture with a positive charge and a picture with no charge. So in fact, carbon-2 only really has a partial positive charge if you blend these together. So that's why it's okay to put that positive charge on the carbon. So in fact, the positive charge here is really being spread between carbon-2 and the nitrogen. The positive charge is really being spread between carbon-2 and the nitrogen. That's why it's okay. Nature likes to spread out charges. It's like, I don't know, if you have, like, say, some hot sauce, you wouldn't want to put all the hot sauce, you wouldn't want to, like, eat a spoonful of hot sauce. It's too concentrated. But if you mix it up and spread it out over your whole dish, then it's tolerable. So the positive charge here is like the hot sauce. It's not tolerable if it was all right on carbon-2. But if it's spread out over a bunch of different atoms in the molecule, that's acceptable. Okay.
Yeah.
So let's see. Okay, so that's what we got from this. In fact, it turns out that resonance is a very strong effect. A primary carbocation that's resonance stabilized is probably preferable to a secondary or maybe even a tertiary that's not resonance stabilized. Resonance is more important usually than other effects. So this primary carbocation is actually probably even more stable than a secondary or maybe even a tertiary that didn't have the resonance stabilization. Okay, good. Okay, so let's try drawing new electron pushing arrows here.
Okay.
Okay, good. So again, now we have a lone pair that's on an atom that's attached to carbon-4 with a positive charge.
Yeah.
So what might we predict about reactivity here?
It doesn't really look very reactive. Well, actually, that nitrogen could be nucleophilic. It has a lone pair and even a negative charge there that it could be nucleophilic.
Okay. On the left-hand structure, the nitrogen has a negative charge. In the right-hand structure, it has a lone pair. We would usually expect that to make it nucleophilic. Okay, good. Any other atoms that we might expect to be reactive?
Well, yeah, you could potentially have carbon-4 be an electrophile because it has a positive charge on the structure on the left.
Okay, good. I think I'll go back to my screen. So in this picture, what role would you expect carbon-2 to play?
Electrophile.
Let me actually use the same numbers that you did. 1 second. So in this picture, what role would you expect carbon-4 to play?
Electrophile.
And why is that reasonable?
The positive charge.
Good.
The carbocation.
And in this picture, what role would you expect carbon-4 to play?
It could also play electrophile.
And why would that be reasonable in this picture?
It seems analogous with the carbonyl carbon. That's typically a good electrophile, carbon-4.
Okay, that's good to see that analogy. It's good to see that it looks similar to the carbonyl carbon. But let's try to be a little bit more specific. Remember that we have specific rules for when things are electrophilic or nucleophilic. So what would be a specific reason why carbon-4 would be expected to play a certain role here?
Because of the delta positive charge.
Okay, yeah, that's the reason why carbonyl carbons are electrophilic. Okay, so that's important to keep in mind.
Okay.
If you don't see a positive formal charge, you look for delta positive charges to look for an electrophile. Okay, so it seems like we have a dilemma. We're not sure whether the nitrogen will be the nucleophile or the carbon will be the electrophile. There's actually a pretty clear-cut way to resolve that issue. So let's start with this picture. Let's say we just focus on this picture on the left. You're saying this might be a nucleophile with its negative charge, or this might be an electrophile with its positive charge. It actually has to be carbon-4, though, that's going to react. And maybe I'll get rid of this arrow now so we can analyze this more. Because carbon-4 doesn't only have a positive charge, it has an incomplete octet.
Okay.
It doesn't only have a positive charge, it has an incomplete octet. If this nitrogen acted like the nucleophile, we would still be left with an incomplete octet on carbon-4. Well, nature is not going to want to just hang around with this incomplete octet on carbon-4. So carbon-4 here is more reactive than the nitrogen, because it really needs to get rid of not just the positive charge, but also the incomplete octet. So to review, what have we decided? In this picture, who would be the reactive atom?
Carbon-4.
And what role would it play?
Electrophile.
So in this picture, we would expect carbon-4 to act like an electrophile, like this.
Yeah.
Okay, because we need to get rid of the incomplete octet. Now, how about this picture? Well, what role did we expect carbon-4 to play in this picture?
Electrophile as well.
Now, is there a possibility in this picture that we would of the nitrogen being nucleophilic?
Yeah, it's possible. It seems that has a lone pair that could be, and there's no incomplete octets.
Okay. Now there's one more thing I think you've forgotten to apply here. In this picture, the nitrogen would be a neutral nucleophile. Now, what happens to a neutral nucleophile after it attacks?
Oh, you're right. It would need to lose a hydrogen.
But it doesn't have any hydrogens.
Nope.
So would we expect the nitrogen to be nucleophilic in this picture?
No.
So what reactivity would we predict from this picture?
Also carbon-4 as the electrophile.
So notice, just like in the previous example, there was no contradiction between these two pictures. If we really think about it carefully, in both pictures we expect carbon-4 to be the electrophile. Notice that in this picture, for carbon-4 to be the electrophile, we'd have to make room. This would have to act like a kind of a pseudo-leaving group by pushing the electrons up to here, like in a carbonyl. Okay, so sometimes the two resonance structures really give you the same prediction, if you think very carefully about the rules that we've talked about earlier. This resonance structure would have predicted carbon-4 would be electrophilic and not the nitrogen, because it's more important to get rid of the incomplete octet on the carbon than to get rid of the negative on the nitrogen. And this picture would also predict carbon-4 would be the electrophile and not nitrogen the nucleophile, because neutral nucleophiles, you usually can't have a neutral nucleophile if it doesn't have a proton, because it wouldn't be able to get rid of its positive charge. Okay.
Okay.
So what reactivity would we predict here?
Electrophile on carbon-4.
Yeah. So in a way, the resonance didn't help us that much. It was the same prediction as before. What type of carbocation is this? Primary, secondary, or tertiary?
Secondary.
But it's more stable than a normal secondary carbocation. Why is that?
Resonance stabilization.
Right. In fact, this would have been more interesting if I had done this. What type of carbocation is this?
A primary carbocation.
So does that mean it's illegal?
No, because it's stabilized by resonance.
Yeah. So here, the interesting thing is that the resonance would show us that it's possible to have a primary carbocation here because it's resonance stabilized. Okay.
Okay.
Okay, so we did a couple of examples now of this rule of a lone pair on an atom that's adjacent to a carbon with a positive charge. So let's look at another pattern. So here's another pattern to recognize for drawing resonance. A pi bond on an atom that's adjacent to a carbon with a positive charge. Tell me when you have that down.
Okay.
Okay, so let's try drawing reasonable electron pushing arrows here on your screen.
Okay.
Okay, good. So those are good electron pushing arrows. I'll go back to my screen. Would this have been a legal arrow?
No.
What's wrong with this?
You are trying to create a pi bond with a carbon that already has a complete octet.
So you can see why the positive charge is important. Pi bond
Yeah.
by itself can't move unless there's room for it to move, like into
Yeah.
a positive charge. Notice that this arrow makes sense because the electrons are moving towards a positive. That's what we would normally expect, for electrons to move towards a positive. And for that matter, notice that this is kind of acting in a semi-nucleophilic fashion. This carbon-carbon pi bond is acting in a way, it's not really nucleophilic because it's resonance, not a reaction, but it's similar to how a nucleophile would react. So it seems like a reasonable arrow. Okay, good. Okay, good. Now, what type of carbocation is this? Primary, secondary, or tertiary?
Primary.
It's primary. Does that mean that it's illegal?
It's only illegal when it's not stabilized by resonance.
True. So is this legal or illegal?
This one is legal.
Because it is resonance stabilized. That's right. All right. So that's one advantage of the resonance here. If you hadn't studied resonance, you wouldn't think that this was a possible picture. But we know this is possible because it's resonance stabilized. And what reactivity would we predict here?
It looks like you could have an electrophile on either carbon 2 or carbon 4.
That's right. We would expect 2 or 4 to be electrophilic. Good. We would expect 2 or 4 to be electrophilic. One of the topics that's usually studied early in the second semester is learning how to predict when carbon 4 is the electrophile and when carbon 2 is the electrophile. I think that's a topic. So that's something that you would go into more detail in the second semester. But what we've talked about so far, we would expect either 2 or 4 to be electrophilic. Notice how that's important. If you just looked at this picture, you'd have no idea that carbon 2 was electrophilic.
Yeah.
If you just looked at this picture, you would think, if anything, carbon 2 would be nucleophilic because of the carbon-carbon pi bond. So notice that the resonance completely changes how we think about this pi bond.
Yeah.
What role do we expect carbon 2 to play in this picture?
Nucleophile.
Because of the carbon-carbon pi bond.
Yeah.
But what role would we expect carbon 2 to play in this picture?
Electrophile.
Even though it still has a carbon-carbon pi bond, because the positive charge is more important, this hidden positive charge. So again, the resonance is very important for revealing the hidden charges. It gives the molecule a whole different reactivity than you would normally expect. And it gives atoms a whole different reactivity. By the way, would you expect carbon 3 to be electrophilic?
No, I don't think so.
Because there's no resonance structure where it has a positive charge. So this shows how powerful resonance is. By moving the arrows exactly correctly, we can predict the exact atoms that will have the charge. This should seem obvious, but if you hadn't studied resonance, you'd have no idea. You might think carbon 3 should be more electrophilic because it's closer to the positive charge in this picture. You might think carbon 3 should be more electrophilic than 2 because it's closer to the positive charge in this picture. But now that we know the rules for drawing the resonance arrows, we can see the positive charge kind of skips over carbon 3. Okay, yeah. Good. Okay, let's try drawing reasonable resonance arrows here.
Okay.
Excellent. Okay, so I didn't specifically ask for this, so it's good that you went the extra mile and you saw there was more than one resonance structure here, and you drew the exact right numbers. That's very good. Okay, so we actually ended up with 4 different resonance structures. This is a case where it's definitely important to number all the carbons to make sure we're getting the same structure in each case. Okay, so what reactivity would you predict here?
It looks like carbons 1, 3, 5, and 7 could all be electrophilic because of the positive charge.
So we would really expect a mixture of products here.
Yeah.
There's not much to choose from between a bunch of these, so we would expect a mixture of products with attacks on a bunch of different carbons here. Okay, good. And it's good that you knew when to stop. You were using the pattern of a pi bond on an atom that's attached to an atom with a positive charge, but you weren't able to find any more examples of that when you got to the end of the structure there, so you stopped at the right place. Okay, very good. Now, in the left-hand picture, what type of carbocation do we have? Primary, secondary, or tertiary?
Primary.
So is that possible or impossible?
It's possible because of the resonance stabilization.
Yeah, normally a positive primary carbocation is not allowed, but it's okay when it's resonance stabilized. In fact, it's just fine in that case. Good. Okay, very good. I'll go back to my screen.
Okay.
Okay, let's try drawing some reasonable resonance arrows here.
Okay. Okay.
Very good. So how many resonance structures does this molecule have? What's the total number of resonance structures this molecule has?
3.
Good. So I think as you're noticing here, the way we drew it is a little misleading. You might think there were 4, but one of them was just drawn twice. So that numbering approach you used was a smart one. That numbering approach was a smart one to show that there's really only 3 separate resonance structures in this case. I'm going to go back to my screen. So I think what you saw here is that there was a little bit of a dilemma at the beginning, because you can either do this or you can do this. So maybe you just arbitrarily decided to do this first. Now, this made things a little bit awkward because then you kind of wanted to go back and do it the other way.
Yeah.
And that's perfectly okay, but the problem is then we ended up drawing this resonance structure twice. That's kind of a little bit unelegant. And it also it could suggest that this is a separate resonance structure when it's the same as this one. So the method you came up with was a pretty good one, especially I liked how you numbered them to show there was really only 3. But there really is a better approach, which is this, to show that third resonance structure. This is just a little bit more elegant because this way we don't have to recopy and start from scratch again, if you see what I'm saying. This way we can just have each resonance structure be a continuation from the previous one. So this is probably a preferable way to draw all the resonance structures. Rather than going back and recopying this molecule and showing this approach, we can actually get to the same structure by putting these two things together. Try drawing this on your screen then. Try drawing what would be the product from these arrows, or what would be the new resonance structure from these arrows. Try copying this way onto your screen and then drawing the third resonance structure.
Okay.
Let's see, where are we?
So right up here is the
okay, good. Okay, notice you get the same results as you did before, right?
Yeah.
Okay. Now, I'm not saying your way is wrong. Your way is not wrong. You wouldn't lose credit for it or anything. This is just a little bit more typical or more elegant. It's a little bit safer because this way you only draw 3 structures. You don't have to number them to show that there's 3 of them.
Yeah.
But, you know, your solution was actually a good solution, too. So this is not really a big deal either way. The way you did it would work as long as you kept in mind that one of the structures was drawn twice and that you numbered to show there's only 3 separate ones. But it's good to see that you can kind of put more than one arrow together here. This is the first time that I think we've done an example with 2 resonance arrows in the same picture. Earlier we were always drawing only, I think, 1 resonance arrow in a picture. Or maybe actually that's not true. That's not true. We've done some other with 2. But in any case, this is a case where it helps to put 2 in the same picture. Okay. Like I say, I think this is a good approach, but the approach you came up with was actually a pretty good approach too. All right, so let's see. In any case, this follows the same general pattern of a pi bond next to a carbocation. Let's try to come up with some resonance arrows here.
Okay.
Okay, very good. So you kind of switched to a different pattern here. So your first arrow, you went back to the previous pattern of a lone pair on an atom that's attached to a carbon with a positive charge. You used that pattern to draw the new resonance structure. And then you drew some new arrows. Those arrows don't quite follow into any of the patterns we've talked about so far, but it turns out they are still reasonable arrows. So you came up with some good arrows here, and you ended up with your product. Okay. So those are good. Those are all reasonable arrows. I'll go back to my screen.
Okay.
I just wanted to show you another way you could look at this. On this problem, you could have drawn this arrow first. On this problem, we could draw this arrow first. Try it this way on your screen. Let's not erase your previous work. Let's just try it again, like this.
Okay.
This fits more into the pattern we were just talking about of a pi bond on an atom that's connected to an atom with a positive charge.
Okay.
Excellent. Notice that matches your third resonance structure from your up above. Now, how can we get a third resonance structure this way? Try to draw some new electron-pushing arrows in this picture. That will give us a third resonance structure. And that matches the picture that you drew as your second picture up above. Okay, so the way you did it above is perfectly fine. Neither of these is preferable to the other. I just wanted to show you both ways. But either is perfectly okay. The way you did it the first time is just fine as well. All right, so what would we predict here about reactivity?
Well, carbon 2 seems very electrophilic. And carbon 4 also appears electrophilic. Carbon 2 could be, in some resonance structures, as a carbonyl carbon, which tends to be electrophilic. And it also, in another resonance structure, has a positive charge as a carbocation, and that is also electrophilic. Carbon 4 has a positive charge in one of the structures, which would be electrophilic. The oxygen on 2 of the structures has a negative charge, which is electrophilic or basic.
Say that one more time.
The oxygen with a negative charge that shows up on 2 of the resonance structures would make it nucleophilic or basic.
Good.
So I'm not quite sure which direction it would go. It may depend on what it's reacting with.
Okay. So basically here what's going to happen is that either 2 will be the electrophile or 4 will be the electrophile. This is going to be one of the topics you study in the second semester. Either 2 will be the electrophile or 4.
So you have the incomplete octets. So oxygen would not tend to be the nucleophile, because if it were, you'd still, or nucleophile, I mean base, because to be a nucleophile it would need a hydrogen. But it would not necessarily be basic, because you would still end up with a carbocation, an incomplete octet. So the preference would definitely be on carbon 2 or 4 as an electrophile.
Okay, that's good. That was the next step in the logic you hadn't been taking a second ago. So that's good that you were thinking about that. That's correct. That's what I was going for here. So yeah, we would expect 2 or 4 to be the electrophile here. And you just have to study in more detail. Some reagents prefer to attack 2, and some reagents prefer to attack 4. This will be one of the topics that you would see in the second semester. Let me go back to my screen. So let's analyze this more slowly, although what we've been saying is correct. So let's just take these one structure at a time. What reactivity would you predict just based on this picture?
Carbon 2 as electrophile.
Why would you say 2 would be the electrophile rather than the oxygen be the nucleophile?
Well, there's an incomplete octet, carbocation, and oxygen does not have a hydrogen to lose for it to attack nucleophilically.
Okay, the first thing you said was correct. The second thing wasn't quite correct. Negative nucleophiles don't need hydrogens.
Oh yeah, that's right. Okay.
Because they are not going to have a positive charge after they attack. Okay, so only neutral nucleophiles need hydrogens. After all, we've seen many, many examples of negative oxygens that were nucleophilic. So the point is it's a neutral nucleophile that needs the hydrogen. Okay, so the first thing you said was correct. This can't be a nucleophile because that would still leave an incomplete octet on carbon 2. Nature's top priority here is to get rid of the incomplete octet on carbon 2. Okay, so here this structure would predict 2 would be electrophilic. How about this structure? What reactivity would we predict from this structure?
Carbon 4, electrophile.
Because of the positive charge.
Yeah.
Why wouldn't you predict the oxygen to be nucleophilic?
Because you'd still be left with an incomplete octet on carbon 4.
You were already seeing that earlier, so that was good. Now, what reactivity would we predict from this resonance structure?
Carbon-2 as electrophile. It's got a delta positive charge.
Good. Here, carbon-2 would be predicted to be electrophilic. Anything else? Why would we not predict the oxygen to be nucleophilic?
Because as a neutral oxygen, it would need a hydrogen to lose in order for it to be a nucleophile.
Okay, that's the right logic. In this picture, it would need a hydrogen to be a nucleophile because now it's neutral. So notice all three pictures agree the oxygen will not be a nucleophile.
Yeah.
All these pictures agree the oxygen will not be a nucleophile for various reasons. There is another role the oxygen could play in this picture.
Base?
Yeah, weak base.
Weak base.
So for example, what would happen if we did this under acidic conditions? We might start by protonating the oxygen. That would be another possibility in this case. I don't know, does that come up too much? Probably, actually, I don't know if that even comes up much though in the reactions you'll see, so maybe that's not worth mentioning. Okay, so here's the main reactivity we would expect here. So overall, what reactivity do we predict combining all three resonance structures?
Electrophile?
For which atoms?
2 and 4.
Yeah, 2 or 4. Now, you might think that 2 is more likely to be electrophilic because there's 2 structures where it's electrophilic, but sadly that logic doesn't work. Actually, most of the reactions you study in the class, 4 would be electrophilic here. Remember that when there's more than one possibility for who can be reactive from different resonance structures, it's really hard to predict just from looking at the structures who will be preferred. You can't just say that the one that appears in more structures is the one that's preferred. Unfortunately, it doesn't work that way. In reality, almost all the reactions you'll study will have carbon-4 being electrophilic here, although there are a couple where 2 is. So basically, we just can't predict from what we've learned so far who will be the electrophile, 4 or 2. It just depends on which reagents you use. It depends on what reagents you end up using. Okay, and you'll study that in more detail when you go into that reaction, but at least now we can predict. So if you looked at this picture, a naive student would just predict that the carbonyl carbon would be electrophilic. They'd have no idea that carbon-4 was electrophilic. So that's the bonus from knowing about resonance, the resonance here. And the same from this picture. We started with this picture, actually. If you started with this picture, a naive student wouldn't have predicted that carbon-4 would be electrophilic, but now we see why that's happening. Okay? Good. You might have predicted that carbon-4 or 3 would be nucleophilic because of the carbon-carbon pi bond, but that's not going to happen because there's resonance structures where it's positive. If there's a resonance structure where you're positive, you're not going to be nucleophilic. All right? Yeah. Let's see. Okay, so would this be a reasonable electron-pushing arrow?
No. Oxygen has a complete octet, so there's no room for it to form a pi bond.
Okay, good. So I just wanted to remind you that's why in this rule, it's not good enough for the pi bond to be adjacent to a positive charge. It has to be adjacent to a carbon with a positive charge.
Okay.
Good. So let's try drawing some electron pushing arrows here. For resonance.
Okay.
Okay, very good. So this is just a review of an earlier pattern. This is the pattern of a lone pair on an atom that's attached to an atom with a pi bond. Just to review that. Good. So what reactivity would we predict here?
Carbon 3 as a nucleophile or base.
Good. Anything else?
The neutral alcohol could be a nucleophile or a weak base. Although that seems unlikely because one of its resonance structures has a positive charge. But
right.
I'm not quite sure.
So to clarify that, if there's a resonance structure where you have a positive charge, you're not going to be nucleophilic.
Okay.
If there's a resonance structure where you have a positive charge, you're not going to be nucleophilic. Okay, so actually your first answer where you stopped earlier was correct. Really, we would expect here carbon 3 to be nucleophilic. We would not expect the oxygen to be nucleophilic because it has a resonance structure where it's positive. Okay, by the way, this compound on the left, this is what's called an enol. That's another of the key topics in the second semester, enols. So we can see here that enols tend to be nucleophilic, and the nucleophilic atom is carbon 3 in this picture. Okay, so that's about our time for today. So remember what we've been doing is going over the 5 patterns to recognize for resonance, and we're doing all right. We've gone over 3 so far, and we have 2 left. And then we'll have kind of seen how to draw resonance structures, and I think you've been picking this up pretty easily and pretty quickly, so I decided not to just go over this, but because you were picking this up pretty quickly, we've also been going into how to interpret the resonance for each of these as well. We've been seeing how the resonance reveals hidden charges that predicts new types of reactivity or different types of reactivity than we would have expected before. We saw other important things about resonance, like, for example, it can help to stabilize primary carbocations that normally could not have been formed. So we've been going over the patterns for drawing resonance, but because that seems to be coming pretty easily to you, we've also been going over how to interpret the resonance as well. So so what's left is to go over the 2 other patterns and keep going over how to interpret those as well. All right, so like I said, I think we're making good progress. I felt like you were picking up this material pretty quickly, so that's good. One thing to keep in mind, though, is even though I think we made some good progress, we've actually covered a lot of material so far, and it would be easy to start forgetting it. So it's important for you to keep making the time of carefully reviewing. We've actually covered lots and lots of rules and lots of exceptions, and I think right now you have a pretty good grasp on it, but it takes constant review to avoid starting to get those things confused in our mind. So I'll just recommend keep reviewing regularly, for example, the first 2 pages of this handout. The first 2 pages of this handout actually covers a lot of material, so it's important to keep regularly reviewing that. We saw how it was, there were a couple slight misrememberings here. For example, we have to remember pi bonds are not nucleophilic, carbon-carbon pi bonds are nucleophilic. And something that isn't on here, but we saw, it's not true that nucleophiles need to have a hydrogen. Neutral nucleophiles need to have a hydrogen. So we've covered, so like I say, overall I think we're doing quite well here, but you can see that when we've covered so much material, it is easy to start forgetting or confusing some of the ideas. So I just recommend keep reviewing carefully because you don't want to lose the good progress that you've made so far. But right now I think we're doing pretty well.